Hello, going to go through the formula sheet and tables here that are usually in the AP exam packets and could be helpful for you on the AP exam, and just making sure that you know how you'd use each formula. Beginning here, right up top, this is just a simple mean formula, add them up, divided by how many there are. This, along with the standard deviation formula, this is a standard deviation for a sample. Okay, both of these you'll almost certainly use a list and then stat calc one variable stats if you were ever to need those, rather than finding them longhand using those formulas. But that's mean and standard deviation. Right here's your regression formula, y hat equals a plus bx. Again, what you would most likely need with that is to write the equation. You do need to define what y hat and x would stand for. Or you may be asked to interpret slope and intercept. And again, A is going to be your intercept here, which is that top left in the computer printout. B would be that slope. This formula and this formula here, right now, I wouldn't worry too much about those. You'd have to be given pretty specific values to use those. And what it would be is essentially they'd give you 3 out of the 4 values in each of those as ways to find slope or intercept, or the x or y bar values. Or down here, this is with correlation and what it has and how it relates with to the standard deviation for the x values and the y values. This here is the correlation formula. Most likely, the correlation formula would be something that you'd probably use your calculator as long as your diagnostic is turned on, and use a linreg StatCalc 8 on your calculator to get the correlation. Or it might just ask you most likely to either interpret R or interpret R squared. So that formula would be pretty rare to use. Here are your two probability formulas that came from our second to last unit in our curriculum. In this case, in this first one here, you're looking at situations where you are given 3 out of the 4, or you may have to find the third. For instance, if it says they're independent, then the probability of A and B equals the probability of A times the probability of B. So that would allow you to get that, and you'd be solving for the A or B here. Again, that U means union, and that is really an or statement. And this here is intersection, which is an and statement. And again, here you just have a scenario where you can essentially find all but one, and you would be solving for the last value. This here would be a situation that would kind of mimic maybe a Venn diagram. Might be the picture that corresponds to that. And then here you're looking at that conditional, that A given B, and if they aren't independent, and how they relate. And here it's about really establishing what in the problem is A and what in the problem is B, in that conditional. Here, these two formulas. This is the mean and standard deviation. If you get a table like this that has maybe 0, 1, 2, 3, and it has a certain probability there under it. So these two formulas here would be the mu and the sigma for that. And then again, those may go into rules for means or variances, or you may use those in a z formula, as an x minus mu divided by sigma formula. The binomial scenario, again, if there's a fixed number of trials and it's looking for a certain number of successes, whether that's 10 free throws and it's looking for exactly 7 makes, or maybe it's at least 7 makes or at most 7 makes, that would just be iterations of this formula. If it's exactly 7, then it'd just be the n would be 10, and the x here would be 7, and maybe you're a 65% free throw shooter, so the p would be 0.65, and you just fill in the values in the formula. Again, if it was at least 7, then you'd need this formula with x being 7, 8, 9, and 10. If it was at most 7, you'd need that formula with x being 0 all the way up to 7. And again, you don't need to write all of those, but you should write at least the first and the last with a plus dot 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 plus in between them to show that that formula continues on. This is to find the mean for a binomial, and this is the standard deviation for a binomial. And again, if n times p and n times 1 minus p are both 10 or more, and if 10n is less than capital N, meaning there's independence, then these mu and sigma values could also be used in a z formula with x minus mu over sigma. Geometric right below that. So the geometric here is the scenario where you go until you get a success. So again, just like with the binomial too, there may be a table like this. Difference is a binomial is the number of successes on the top row. So that would start at 0 for a binomial right here. But for a geometric, it's actually the number of tries until you get your success. And again, that could be an infinite number of tries in theory. So the binomial one, the table would have an end, the geometric it wouldn't. But you'd essentially, if it was how many free throws until you make one, you would just multiply up however many fails you have. And so if we use that p equals 0.65, again, it would just be 0.35 would be the fail. And you just multiply 0.35 for however many misses you have. And then whenever your make is, this would be the situation where your first make is on your 4th try. So that's that formula in action. Again, this is just 0.35 to the third, which is what that formula is suggesting right there with 1 minus p to the x minus k. Sorry, x minus 1. Here's your mean and standard deviation formula for a geometric. Okay, down to the sampling distributions and inferential statistics. So a standardized test statistic. For us, this is really, it started out, if there was a situation where the distribution was normal, like ACT scores or something, then it was x minus mu over sigma. Okay, that was x is the statistic, mu would be the average ACT for all Minnetonka High School students, sigma would be the standard deviation. Then we moved on to scenarios where we had to use the sampling distribution to get an approximately normal distribution. And in that case, it was x bar minus mu divided by sigma over root n. Again, this is scenarios now where n is greater than 1, as opposed to over here where n was equal to 1. Okay, this is, you could technically say, is over root 1 right there, in the same vein. But now it's x bar because there's an average for your x's. It's not just a single value. And again, this would be a scenario where you maybe have the chance that 10 ACT scores have an average of over 30, which of course is much different than just one student getting an ACT score of over 30. So what happens is in the sampling distribution, that spread, that variability decreases. And so the chances of getting far from the mean become less, and the chances of getting close to the mean become greater. For instance, if the average ACT in our school is 27, when the sample size is 1, that graph is really ranging from the low teens up to 36. But if the sample size is, say, 20, then you're not going to get 20 students who have an average ACT in the low teens or 36. So that will end up being closer to that 26 to 28 range for most of those averages. The one other area that we saw this, actually a couple of, I guess, we had the p hat minus p, and then p1 minus p over n as the standard deviation, was also a z. And then lastly, we did also have the t here, which was x bar minus mu divided by s over root n. Okay, and those were all of our one sample options. And then we did have the two sample options as well. And the two sample options, again, would be for the t here, you'd have x bar 1 minus x bar 2 all over s sub 1 squared over n1 plus s sub 2 squared over n2. Or for the z, you'd have p hat 1 minus p hat 2. And this one, typically we'll see this with the p hat pooled or combined now for this one. And again, these are all different iterations of statistic minus parameter over standard error. Confidence interval. For the confidence interval, they just correspond to these here. So the confidence interval for, let's go with red here, confidence interval for the proportions was the p hat plus or minus z star times the p hat and 1 minus p hat over n. Okay, so that's confidence, that statistic is the p hat, critical value is the z star, and then the standard error is that p hat times 1 minus p hat over n, all square rooted. And then there was for the t, the confidence interval was x bar plus or minus t star times s over root n, which again is statistic plus or minus critical value times the standard deviation over the square root of n, which is known as the standard error. Then again, s is the standard deviation, but when you divide by the root n, it becomes standard error. And then the whole thing here after the plus minus is the margin of error. Okay. And then there's the two sample confidence intervals as well, which is getting pretty busy. I won't write them on here, but there's a two sample confidence interval for proportions and for means. The chi-square formula is actually not on the 2020 exam, but there's the chi-square formula. That's everything right there included. And again, in this case, the summation means you'd have to write at least the first and the last with a plus dot 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 plus in between if you have a bunch of formulas. On the back side here, now we get to all the specifics. Here's the proportion information. So we've got the sampling distribution. So this is the center and spread for a sampling distribution of proportions. You can see when it make it a sample statistic, then the sigma becomes an S there. But this would be, again, this is the P and P hat minus P. This is the denominator, is that standard error formula there. This is for the two proportion, it's the P1 minus P2, which you saw like P hat 1 minus P hat 2 in the two proportion tester interval. Here's the standard error formula that you would use for a two proportion Z interval. And here's the standard error formula that you would use for a two proportion Z test. And again, that C stands for combined there, which means you just take the numerators and add them up and the denominators and add them up of the two samples and then get that proportion, and that's your P hat combined there. So this is all the information on proportions. Describing a sampling distribution again would be you'd have center and spread, and then what you'd be looking for is that n times p and n times, n times p and n times 1 minus p, both being 10 or more if it's a one sample, 5 or more for each if it's a two sample, but that's what would ensure an approximately normal sampling distribution. So if you were asked to describe a sampling distribution for proportions, there's all your information. Similarly, if you were asked to describe a sampling distribution for means, there's your information there. Again, we'd like n to be 30 or more here to ensure an approximately normal sampling distribution. If it's a sample, then it's S sub x, x bar there. Here's what we would use as our standard error formula for the two proportion interval and the two sample t interval and two sample t test. This is again for populations over here with the mu's, but center, spread, and shape would be related to sample size there for the sampling distribution. And then over here, we get all these formulas that show up in the intervals in the tests. The bottom part here, again, this is for the slope. So we don't see this on the 2020 exam. That's just population slope and then some values there regarding the standard deviation of the residuals. Moving to the tables. First table here, Z table. You will just most likely use the normal CDF, lower bound, upper bound here under second bars on your calculator or distributions. Again, lower bound, upper bound means if it's a less than, it's negative 99 to that value. If it's a greater than, it's going to be that value to 99. So if it were this, it would have been that value to 99. But that's the Z table, so you most likely will just use normal CDF there. The next one, the T table. This one you may use. Again, you do have to be aware of, are the degrees of freedom in the problem included here? And if they aren't, you aren't really expected to go find these values, but these are all T star values here that you would use in a one sample T interval. Two sample T interval, you probably wouldn't use these because if you do it on your calculator, you're going to get some unusual degrees of freedom, and it probably won't be on the chart. Again, for degrees of freedom in a one sample, it's just one less than the sample size. In a two sample, it's going to use a more complicated formula. And if you get to a part of this table where it starts to go up by tens, again, you have to round down. So if your sample size is 60, you'd have 59 degrees of freedom in a one sample interval. And you'd have to go up to 50 degrees of freedom because you can't go back up to 60 because that's presuming more accuracy than you have. And then just a reminder, this bottom row, this infinite, these are the Z stars. Okay, so for proportion intervals, these would be your Z stars. So if it's a 95% confidence interval, there's your 1.96 Z star, and then all these up here would be your T stars. Keep in mind, interval's dead center, so that 95% is in theory really referring to the middle 95%. Sorry for that curve. And that's why this is 0.025 there, is it's really just recognizing how much is left in each tail for in a 95% confidence interval scenario. Um, and with 90%, then it's 5 and 5 on each side and so forth. Last table is the chi-square table, which again is going to have the degrees of freedom. The unique piece on the chi-square is that it's going to always be area to the right. And so in this case, so the T-CDF was much like the normal CDF, except we added in degrees of freedom. The chi-square CDF is always going to be your test statistic, and then some big number, and then degrees of freedom. And so for that reason, essentially, if it's a 5% alpha or alpha 0.05, then we look at this as kind of being our rejection region over here and our fail to reject region here. So again, don't forget the calculator functions can help with the tables for that TCDF, lower bound, upper bound, degrees of freedom. And again, negative 99 or 99, if you're shading all the way down to the left or all the way up to the right, can be your lower bound or upper bound respectively. On the chi-square, because it always shades to the right, we go with that test statistic up to 999 and then the degrees of freedom there. And then that goes on with bigger degrees of freedom along the way. Thank you very much for listening. As always, please ask questions if you have them. Thank you.